Well, and it is 12:01 or 12:02, so I will pass this on to today's moderators and commenters to get us started.
Okay, I can get started. So last week, we started off with Elizabeth Leclerc, who studies the Supe Valley of Peru for her master's research. Her research is on the effect of the hydrological variation of the highlands in the coastal watershed of Peru, where she focuses on the relationship between extreme weather events and water management in the archaeological record. Previous studies from the region has found that the depopulation of the Carl region of the Supe Valley aligned with an onset of El Nino, local tectonic events, and aeolian activity. This resulted in a sand invasion that occurred at 3.8 thousand years ago. Elizabeth's work focuses on the limited data of the hydrological variation from 4,000 to 6,000 years ago to better understand the climatic shifts of this period. She's created a geospatial model to divide the region into hydrological units and to then quantify and compare the qualitative flow dynamics of these units. Ultimately, she will incorporate archaeological data, including radiocarbon dates and site locations, to better understand how these hydrological units and vegetation management are linked. Ultimately, her research will help us understand water management resilience in the face of climate change. So moving on to Inga to give us the next summary.
So our second talk last week was given by Erin Hill on quantifying surface changes across the McMurdo ice shelf in Antarctica. The McMurdo ice shelf is a small, thin ice shelf that abuts the much larger Ross ice shelf and helps to buttress or hold back flow in the Ross ice shelf. The McMurdo ice shelf is thinning, both because of subglacial melt due to contact with Antarctic surface water, which is the warmest water mass in the region, and also because of unusually high surface melt, which covers up to 25% of the ice shelf area. Anne presented preliminary results on changes in surface elevation that she obtained by differencing DEMs at two different sites, Hut Point and Cutlets Glacier. At Hut Point, we see thinning along the shelf front and variable elevation change across Hut Point. And at Cutlets Glacier, we see thinning from 2010 to 2011, followed by variable thinning or thickening from 2011 to 2016, depending on whether we're looking at the ice shelf proper or over adjacent land. In terms of next steps, Anne plans to examine spatial and temporal changes in surface melt and also surface velocity, as well as examine grounding line changes in tributary glaciers to the McMurdo ice shelf.
So today I'll be summarizing Erin Chesler's talk titled Decoupled Acid Reactive and Biologically Relevant Iron Concentrations Spanning 5,000 Years in the South Pole Ice Core. His talk focused on new ice core data from the South Pole Ice Core that sheds light on ocean and atmosphere carbon cycling during the last termination. He introduced that iron and dust have significant anti-correlating relationship to CO2 and temperature proxies. However, due to different assumptions of biologically relevant iron between oceanographers and the ice core community, Erin asked the question, does acid reactive iron equal biologically relevant iron concentrations? And then he presented two sets of trace element data, including high resolution and continuous data of the acid reactive and biologically relevant from present to 16,000 years ago, and the low resolution and discrete samples, total acid reactive and biologically relevant from 10 to 50,000 years ago. From the data he collected, he determined that coupled changes in dust size and geochemistry are related to Southern Hemisphere westerly wind strength, and changes in proportion of biologically relevant iron should be related to activation, or could be related to activation and deactivation of Antarctic dust sources. His conclusions consist of the following: that fractional relationships are not consistent between total acid reactive and biologically relevant. Proportionally to the total fraction, acid reactive and biologically relevant iron are affected by different processes. And lastly, changes in biologically relevant iron seem to be affected by particle transport.
So to sum up really quickly, our three talks last week all approached problems related to flow behavior, but of three different media. Elizabeth's work pertains to past stream flow and hydrologic regimes in the Supe Valley and their relation to settlement patterns and water management. Anne examines ice thickness and how it relates to ice flow into and through the McMurdo ice shelf. And Erin is developing the link between iron, particularly the biologically relevant fraction, in spice core and past patterns of atmospheric circulation or airflow. And with that, I will turn it over to our first speaker this week, Peter Strand, who will be discussing the last glaciation and termination documented in the Southern Alps of New Zealand and the Altai Mountains of Western Mongolia.
Thanks, Inga. Let's see if I can get this going. All right, does that look correct on everyone's screen? Yes, I see some thumbs up. All right, thanks Inga for the introduction. I'm actually going to, oh, sorry. For those who I haven't met, my name's Peter Strand. I'm a PhD student in the School of Earth and Climate Sciences. And I'm going to actually be paring down my talk just a little bit in the interest of time. And I'm going to speak about the last glacial termination in Mongolia. And so this research is part of my overall research goals, which is to understand the last glacial termination around the world. So last glacial termination is time period about 18 to 20,000 years ago. And this global warming brought the end to the last ice age. So this was felt all around the world, and it was just part of the natural variability of the Earth's climate system. And so we want to understand the timing, the magnitude, and the signature of this event at different points around the world. And in so doing, we can hope to, make better predictions about future climate change by understanding the natural climate variability. And so in order to answer that question, I've been reconstructing glacier chronologies of various mountain glaciers around the world. Here are a few of study areas that I've been working on in Asia. And we use mountain glaciers as our climate proxy because they're relatively simple physical systems, and they respond primarily to changes in atmospheric temperature. So everyone can picture a glacier, and when I say a mountain glacier, that's one that's confined by topography as opposed to, say, an ice sheet. And so as climate cools or warms, these glaciers grow or melt, and by reconstructing their former geometry and their size, we can reconstruct local climates in these areas. So the study area today is located in Western Mongolia, in this red box here, in the Altai Mountains. Altai Mountains span geopolitical boundaries of China, Mongolia, Russia, and also Kazakhstan. We've traveled on a number of expeditions to Western Mongolia, most recently in 2019, last summer, before, well, when travel was still possible, I suppose. And focused primarily on this, what's going to be known as the Hotan Nur area, this system of lakes and the former glaciers that occupied those valleys. Western Mongolia is a very remote place. Takes some doing to mount an expedition out there. We rely heavily on our Mongolian guides as translators, cooks. They keep us safe and help us get where we need to go. Just in the background here, it's an example of a Mongolian road. So it's a very remote place. To get up into the mountains, you can only drive so far, and then we transfer to horse and camel transport to get up to some of these glaciers. But once we're out there, we observed just these spectacular glacial landforms. In the foreground here is a ice molded bedrock hill. So in this image, the LGM, last glacial maximum ice flow, would have been from right to left. And you can see the lake back here, which now occupies this trough that was carved by the glacier. In the foreground, you can see this polished, glacially smooth bedrock here. And all throughout these valleys are these large granitic boulders. And these, standing on a moraine ridge here, you can see it sort of trending off into the distance. And these boulders are numerous, and they provide excellent targets for beryllium-10 surface exposure age dating, which I'll explain a little more about in a minute. But it's these landforms and boulders which allow us to reconstruct the geometry of the former ice positions, and will provide targets for future glaciological modeling as well. Here's another example of some of these boulders. These are erratic boulders on ice molded bedrock. I like to say, I've shown this image a few times, I like to say that if you squint hard enough, you might even think that you're on Mount Desert Island. Very similar landforms here, but this is in Western Mongolia. And we're also able to get up into some of these high peaks of the Altai Mountains to investigate some of these younger, fresher, potentially Holocene deposits as well. All right, so surface exposure age dating is the tool that we use to create these chronologies, and it works like this. As a boulder melts out of a glacier, such as this one, this boulder, melting out of glacier such as this one, onto a moraine ridge or onto the landscape, it's immediately exposed to incoming cosmic rays from outer space. Now, these cosmic rays, they interact with the atmosphere and set off a whole cascade of chemical reactions, which penetrate down to the Earth's surface. Doing most of the heavy lifting are these high energy protons, which interact with the surface of the rocks, and they set off spallation reactions. In this case, for this talk, I'll be focused primarily on beryllium-10, which I've already mentioned, which is a cosmogenic isotope of beryllium, and it's formed by a spallation reaction of silicon and oxygen in quartz. So this beryllium-10 is found primarily in quartz in those granitic boulders, which I showed earlier. And these beryllium-10 atoms, they accumulate in the surface of the rock once it's deposited on the landscape by a flowing glacier. And they accumulate at a known rate over time until someone such as us comes along and collects a sample of the surface of this boulder. Take it back to the University of Maine, to the laboratory, subject it to a number of chemical procedures to first isolate the quartz and then to isolate the element beryllium. We then ship it off to Lawrence Livermore Laboratory in California, and we can measure the number of beryllium-10 atoms that are in the surface of the rock. And because they accumulate at a known rate, we can calculate how long they've been on the landscape when they were placed there by the glaciers. Let's see, in order to do this work, it relies on a number of people. These are some of our colleagues from the Mongolian University of Science and Technology, some students from there. This is former University of Maine student Mariah Radu. We've also had students, undergraduate students from University of Maine Orono and University of Maine Presque Isle as part of these expeditions. I wanted to put this in because I know there's some archaeologists in the audience, but you can see in this image, this valley, or these valleys in the Mongolian Altai, are home to these beautifully stunning petroglyphs. So these are pecked pieces of rock art, which some of them date back to about 13,000 years ago. You can see them here in the foreground. These depict a number of cultural events in Mongolia and a number of changes over time. For example, the transition to herding animals, and then the transition to a horse-dependent nomadic lifestyle, which still dominates in Western Mongolia. But you can see that these pieces of rock art are pecked directly on these glacially polished bedrock here. You can even see the striations of this bedrock. So we've actually been working with some rock art historians and archaeologists in order to, in a way, provide the age at which the glaciers vacated this valley and presented this canvas, if you will, for people to peck these petroglyphs on. We've also been traveling on these expeditions with students from a high school in Chicago, from the Gary Comer College Prep Institute, and we've been using drones in order to create high resolution maps. So in addition to surface exposure age dating, the mapping is a key part of our field expedition. We can stitch together hundreds of these drone photos and create three-dimensional images, such as this one, and these reveal some of these finer scale glacier deposits. And you can see these thin moraine belts here on this image, and this allows us to place our exposure age dates into context. So again, to the exposure age dates in a second, these are going to be given in thousands of years. So for example, this boulder here dates to about 16,800 years before present, plus or minus 300 years. And so we create glacial geomorphologic maps, such as this one. So that now I'm going to step through some of these results here. In the upper left are some of the high peaks of the Altai Mountains. They're still home to modern day glaciers, although they're rapidly retreating and melting. But during the last glacial period, the last glacial maximum, these glaciers would have expanded, flowing down into these valleys. Multiple glaciers would have coalesced and they would have filled this large basin here, which is now occupied by Hotan Nur, the lake. We actually have observed also some of these more outboard, older landforms representing a much greater glaciation. That was a target of our expedition last year, but I don't have any age results to share from there yet. But what I can do is step through some of the results that we do have. And so this is just a drawing that I made. It's not a model output, but just a depiction of what the glacier would have looked like at this time. Again, here are the high peaks in the upper left flowing down, filling this valley. This glacier would have been about 70 kilometers in length at this time. And we see that it's reached a full glacial position as early as 35,000 years before present. So up in the upper right here is an age population known as a camel plot, sort of a way of showing a statistical analysis of these individual ages from boulders that make up a glacial landform. So 35,000 years ago, this glacier was at a full glacial position. This is about 10,000 years earlier than sort of the classic LGM as defined by maximum positions of the Laurentide ice sheet. And then the next age constraint we have is about 23,000 years ago. This is from the next moraine inboard here, indicating that glaciers were large at this time. So too, about 21,000 years ago, this corresponds to the sort of the classic global last glacial maximum that I mentioned earlier. And then the final position here is given by a series of moraines which pin in the modern day boundary of this lake. And those date to about 19,300, 19,500 years before present. And it's at this time, just before 19,000 years ago, that we think that the last glacial termination in Mongolia began. Because at this time, the glacier began to retreat rapidly. By 18,000 years ago, it had traveled about 30 kilometers up the valley, leaving behind these erratic boulders on the landscape. And then by 16,000 years ago, glaciers had retreated way back into the high peaks of the Altai Mountains, again, as given by these moraine ages here. So we think that time period from just before 19,000 years ago to 16,000 years ago represents the last glacial termination in Mongolia. And it's quite a rapid time. It's a period of about a few thousand years. This glacier retreated about 65 kilometers back into the mountains. And then, of course, the next step, as I mentioned earlier, is to place this into a global context, which we're still thinking about, still puzzling over. But what we can do is compare it to some other global climate mechanisms. For example, carbon dioxide, which was coming out of the Southern Ocean at the time, didn't begin to rise until about 18,000 years ago. So it's possible that this glacier retreat preceded the rise of atmospheric carbon dioxide. This global sea level represents extensive northern hemisphere ice sheets. So by the time the glaciers in Mongolia had retreated far back in the mountains around 16,000 years ago, for example, the Laurentide ice sheet was still quite large. So anyway, I'm getting a little low on time, so I'll just leave it there. And I just have a whole number of people to thank, but including the Dan and Betty Churchill Exploration Foundation for helping out with one of the earlier expeditions, and also the Comer and Casada family foundations. And with that, I'll take any questions that you might have.
All right, any questions?
Just one, the dates you've come up with from this location for the last glacial maximum, if I understand correctly, you're coming up with earlier dates than are generally accepted as the LGM. And so if it did begin retreating earlier in this area, if that's correct, do you have any supposition as to why that is the case?
I don't have any firm answers yet, but that's definitely one thing that we're looking into. I think that the fact that it may have begun, as you said, sooner than than in some other areas of the world might hold some important clues. But no, I don't. That's one thing we're still working on. I don't have any definitive answers as of yet.
Thanks.
Yeah, sure.
Any more questions? All right, then we will move on to Marina Miles. Today she will be talking about differences between land terminating glaciers and marine terminating glaciers since the last glacial maximum in the Royal Society Range, Antarctica. All right, leave it to you.
Thanks. Does my screen look all right? Can you see the slide?
Yep.
All right. Okay, so thanks. I'm here to talk about the interactions between local alpine glaciers and the grounded Ross sea ice during the last glacial maximum. So during the LGM, grounded ice expanded out into the Ross Sea to the continental shelf margin, shown in the red circle here. There are two central ideas as to what caused the expansion of grounded ice in this region. The first is that both local alpine and outlet glaciers thickened and expanded to produce the grounded Ross sea ice. And the second hypothesis, however, local alpine and outlet glaciers did not thicken and may have instead thinned due to colder temperatures, resulting in decreased accumulation during the LGM. In this scenario, the grounding in the Ross Sea was caused by marine mechanisms, such as a lowering of sea level, and interior ice thicknesses remain the same or even thinned. Discriminating which of these ideas is correct is important to understand the driving forces of the Antarctic ice sheet and how it will respond to future climate change. In order to test these ideas, I carried out fieldwork in the Royal Society Range along the Ross Sea. This is an image from Google Earth looking to the northeast towards Ross Island in the top right corner. My field area consists of Walcott, Houchin, and Koettlitz glaciers, all of which are local alpine glaciers. However, Walcott and Houchin terminate on land, while Koettlitz terminates in the Ross Sea, in the area that was once filled by the grounded Ross sea ice. During the LGM, grounded ice filled the Ross Sea and extended landwards to the red dashed line through here, referred to as the headlands moraine throughout this presentation. This limit is higher to the north, indicating that it was deposited by grounded Ross sea ice and not an expanded Koettlitz glacier. This area is important because of its potential for interactions between local alpine glaciers like Walcott and Houchin and the grounded Ross sea ice, which would have filled this area. The goal of my study was to see whether these local glaciers expanded eastward out towards this red dashed line to join the grounded Ross sea ice during the LGM, which would support hypothesis 1, or if they behaved out of phase, which would support hypothesis 2. To carry out this project, I used the following methods. I created a glacial geomorphologic map of superficial deposits, which you'll see in the next slide. I collected samples of subfossil algae for radiocarbon dating. These algae grew in shallow ice marginal ponds and streams along the headlands moraine, the red dashed line in the last image, as the moraine was being built. Therefore, these algae date the formation of the moraine. I also collected samples from boulders, such as this nice perched boulder in front of Houchin Glacier, for beryllium-10 exposure dating. This is the glacial geomorphologic map I mentioned in the last slide. Walcott and Houchin glaciers are on the left and center, and Koettlitz, which again has expanded northward into the Ross Sea to fill the area where the grounded Ross sea ice once was. The grounded Ross sea ice expanded westward multiple times. All right, it's kind of right side of the screen towards the left, depositing units drawn in orange. The darkest orange is the LGM deposit, the most recent one. And outboard of this are deposits dating to stage 6 and older in progressively lighter shades of orange. Alpine deposits are in shades of purple, with the darkest purple being the most recent. This includes deposits along Koettlitz Glacier, which we will get to in a moment. One of the important things this map highlights is that there are cross-cutting relationships in the area south of Walcott Glacier, down in this area. The Ross Sea drift is draped over top of older alpine deposits, indicating that they advanced out of phase with each other. Nowhere do I see evidence that alpine glaciers expanded to join the Ross sea ice, as would be expected if hypothesis 1 is correct. This is a schematic image looking southward from above Walcott Glacier that shows the cross-cutting relationships. The red and orange Ross Sea drifts are draped over top of the purple Walcott drifts, which are alpine deposits. Once I had an understanding of the deposits, I wanted to develop a chronology for the drift units. I'm going to show 2 areas where I have more detailed information in terms of radiocarbon ages. On the left will be this box in front of Walcott Glacier, and on the right will be this box in front of Houchin. I'd like to draw your attention to the dates along the outermost limit of the LGM deposit, out here where the darkest orange meets the next lightest. These ages indicate that the grounded Ross sea ice reached its maximum in the area around 18,000 years ago and maintained its position until at least 14,000 years ago. An interesting point is this date down here by Koettlitz Glacier. This age is from algae within lake sediments that were then thrust upwards by an advancing Koettlitz Glacier, indicating that Koettlitz has expanded in the last 6,500 years during the Holocene. I also collected samples for beryllium-10 dating. Most of the results I have so far are from the area in front of Walcott Glacier. So let's zoom in. So again, radiocarbon ages are in green, and on the left, beryllium-10 ages are in white and blue. The grounded Ross sea ice expanded from the right to the left, reaching its maximum during the LGM around 18,000 years ago. Walcott Glacier, however, has not expanded beyond its limit in the past around 40,000 years. There's no evidence that this alpine glacier advanced during the LGM. Some preliminary conclusions from this research are that the grounded Ross sea ice expanded landward several times, with the most recent expansion reaching its maximum around 18,000 years ago. Alpine glaciers have expanded in the past. However, the most recent expansion was between 35 and 45,000 years ago. Alpine glaciers did not expand during the LGM, and they appear to be expanding at present. This supports hypothesis 2 in the McMurdo Sound region, that these glaciers behave out of phase. This is likely due to marine mechanisms controlling the extent of the grounded Ross sea ice, while accumulation rates control the extent of alpine glaciers. And with that, thank you to everyone, and special thanks to the field team pictured here. And I'll take any questions.
I just wanted to say that I thought that was fascinating and very well presented. I did not understand the different mechanisms involved, so thank you.
Thanks.
Any other questions on the Ross Sea and our glaciers down there?
Yeah, Marina, I had a quick question. Is there much, it's Scott, is there much evidence for marine warming driving grounded ice retreat at the time period you're looking at, or is that just kind of process of elimination? Maybe that's what's causing it at this point.
I think there's evidence at the moment for that happening. I'm not sure what evidence there is of this happening at that point in time. That's something certainly to look into.
Thanks.
Okay, and with that, we'll move on to our third talk. We're going to hear from Edna Pedraza Garzon, and she will be giving a talk called Advances in Lacosera Ecology to Reconstruct Alpine Climate.
Thank you, Megan. I hope you can see the presentation correctly. Can you see it?
Yep.
Okay, perfect. Okay, thank you for attending to this presentation. I'm going to talk about the findings about Lacosera during my research. So for those that are not familiar with Lacosera, this is a diatom or a genus that group cylindrical cell-shaped diatoms with heavily silicified cell walls, and that has an ornamentation pattern in the cell wall. And because these diatoms usually bloom during mixing periods in lakes, and it's believed that the bloom in sediment records is indicative of extended mixed periods. So we can use it to infer changes in temperature. However, the difficulties that have the identification of this group, in particular the wider than tall cell walls diatoms, makes that we have limited information about the ecology of these diatoms, and also difficulties to extract information. So there are doubts about the environmental reconstruction using this group. With this context, the idea of this research was to provide information about the ecology of the species in the Lacosera alpagina complex, which is the most common complex reported in alpine lakes, and therefore it's commonly used for climatic reconstructions. So to achieve the objective, we sampled contemporary ecosystems to identify the factors that affected the species in the complex. And we studied also sediment records of different lakes in the alpine area to establish associations between the occurrence of this species in the complex and the aspects affecting the thermal structure. So we, for the different phases of this study, we analyzed 7 lakes located in the tree line and above the tree line area in the Greater Yellowstone ecosystem. And from our contemporary studies, by the time that we arrived to the Greater Yellowstone area, we had the possibility to focus on Lacosera pusilla, which is also one of the species included in this group. From the surveys and the regression analysis, we found that this species was found in different locations, or better, this species didn't follow the same pattern across the lake that we sampled. So from the regression analysis, testing the effect of conductivity, availability of nitrogen and phosphorus, and the access to light, the analysis allowed us to identify that light was the main factor between these physical and chemical parameters, was the main factor that influenced the location of Lacosera pusilla in these 3 lakes. So with this information in mind, it let us ask if we can use Lacosera to be used as a proxy to detect changes in the lake light axis by shifts in snow precipitation, because snowpack is a factor that determines not only the thermal structure of lakes, but also is the element that gives the starting point of changes in thermal structure by light axis and insulation. And the other question that we had, given the ecological gap that we have about the Lacosera alpagina complex, is if the findings of different species in the fossil record would contrast what we know about the complex Lacosera alpagina. So what we did was to analyze sediment records from 2 lakes to identify the stratigraphic profile of Lacosera pusilla, but we also analyzed or reanalyzed sediments from previous cores that has been studied in the laboratory. We used information provided by 3-ring readings to infer air temperature reconstructions, and also the snow water equivalent values as a proxy of changes in snowpack. And what we found was that for Lacosera piscilla, the trend, okay, this species of Lacosera piscilla was only found in 2 of the 7 lakes that we analyzed. And the pattern for Lacosera piscilla was similar for contemporary sediments for Kersey and Beauty Lake. It peaked in the most recent sediments, and we also found it associated during a time that was identified for Beauty Lake to the medieval climate anomaly. So it gave us a good idea about something that is happening in the lakes that allowed that this species is peaking for the contemporary time. And for Lacosera alpagina, the one that has been used mainly to identify changes in the mixing or in the strength of mixing, we found that for both lakes, there was a different trend, an increasing trend for Kersey, but a decreasing trend in alpagina in Beauty Lake. So these lakes are located at different altitudes, but has also differences in water quality. So it gave us the idea that something happening, I mean, the same event happening in both lakes have a different impact in this species. And from the Beauty Lake profile, we found that the diatom assemblage showed significantly in 3 points. For the oldest sediments, it was dominated by Lacosera alpagina. For the time that we didn't identify, that was dated with the medieval climate anomaly, we found that Lacosera piscilla and Pedraza Garzon, all species that are part of the Lacosera alpagina complex, they peaked during this time while Lacosera alpagina decreased. And for the most recent sediments, again, decreasing trend. Okay, this sediment, this part of the core was the most contrasting because it has periods for the Little Ice Age, and then the most contemporary sediments, they reflect the warming trend. So it shows increases in Lacosera alpagina during times that can be associated with Little Ice Age, and the peaking of Lacosera piscilla for warming trend. The redundancy analysis showed that there are differences in the response of these species associated to variations in snow water equivalent that definitely identify that alpagina has a different or respond different to higher amount of snow compared to Lacosera piscilla or Pedraza that were identified to occur during low values of snow water equivalent. And in conclusion, what we found was that Lacosera piscilla may be a proxy for changes in snowpack, but because we could only find it in 2 lakes, and we cannot still work in with the data that we found for Kersey because it still needs to be dated, and we have problems with COVID things and things like that. We only have information from Beauty. So for now, we say that we think that it could be a good proxy for tracking changes in snowpack. However, the limited distribution of the species that we found in the Greater Yellowstone area suggests that we should include more lakes where this species has been reported to strengthen what we found. Also, because we identified different associations or strengths between the species in the Lacosera distance, Lacosera alpagina complex, and variation to a snow water equivalent. And in the stratigraphic profile, it suggests that there are different conditions that allow the presence of different species in the complex. So it's required to use refined taxonomy for this group. And finally, using the group of Lacosera alpagina without making differences between the species in this group may drive to inaccurate conclusions. So with this, I just want to, I want to give thanks to the program Fulbright, the Shelter Exploration Fund, and to my advisor, my my friends in the Cyrus Lab, and I'm free for taking questions.
Yeah, thank you, Edna. That was really interesting. I'm not really familiar with lake ecology at all, and I'm just wondering if there's many species of freshwater diatoms, and if the Lacosera is still living in the lakes, or if that's just in the sediment records.
Lacosera is indeed, it is the oldest diatom that has been found in freshwater. I mean, it's the only freshwater, I mean, it's only found in freshwater ecosystems. So because we have difficulties to identify them, it's a good group to go deep in research. I mean, we think that the fact that they require mixing to being out of the sediment is something that we can use to get more information about thermal changes in lakes, and also, well, not changes in air temperature, but in the factors that stimulate the mixing in lakes.
Thanks. And so they're still in these lakes?
Yes, they are.
Okay.
The thing is that by the time that we arrived, some lakes were stratified and the others still had snow and ice. So we couldn't we couldn't sample the lakes as we were expecting. You know, we were planning to track the changes in the distribution of Lacosera since or before the mixing until we got the stratification. But when we arrived, some lakes were stratified and the others were still with ice. So it didn't allow us to track all the time that we wanted to study.
Any other questions for Edna?
Well, if there are no further questions, just before I give a few remarks on today's talks, I want to thank all the presenters this semester for really carrying the Bourne Symposium forward in excellent fashion, despite the difficult circumstances under which we find ourselves. So give everybody and each other and yourselves a hand. All right, I do have some comments, as you might expect, on today's talks. I'll start with Peter Strand. Peter provided hordes of data about the last glacial termination in Mongolia. As a scholar of ice behavior, he has been trying to understand how glaciers migrated back and forth in response to climatic change by patrolling the borders of the former ice fields. As a fearless scholar at the cutting edge of science, Peter is using a bolder approach to dating former ice positions via exposure age dating. He also uses rock art to peck away at the minimum age of ice retreat. And as an archaeologist, I appreciated that. In terms of fieldwork conditions, it was interesting to see how Peter and his colleagues humped it into their study area. They weren't just horsing around. Marina Miles explained the thick and thin of glaciers and sea ice in and around the Ross Sea. She grounded her study through fieldwork dating ice records in the region and got into the weeds in describing the dating of algae. Her overriding conclusion is that Ross Sea ice expanded more recently and further than the alpine glaciers, so the two were out of phase. Edna Pedraza's work on Lacosera pusilla diatoms addresses some of the bugs in prior environmental reconstructions using this taxon and associated complex. In taking on this contentious issue, Edna shows that she is certainly not pusillanimous in advancing her research. In terms of response to climate change, A. pusilla and A. alpigena run hot and cold, but under different conditions. One conclusion is that best results will come from being more specific in the analyses. Thank you all, and see you next year.